kick off. So pretty underrated paper here. Also, I don't know if it's underrated. It's just not very popular. It's about kind of LLM as a judge and predicting hallucinations. So the background of picking this paper, we didn't have a paper this week, so I was trying to see what's popular, what's doing well. One of the ones that I was going over was this like agentic memory summary paper. It's very long. It's like 100 pages. Maybe if we have some time today, we can go over it real quick. Um, the problem with that one, I got through it and like they're trying to do a lot of definitions. How do we define what memory is? What are different memories? Throw like, try to explain all these tools and stuff and what classifies as memory versus RAG versus all this. And then hallucination detection and stuff came in, and then this was just one of the top papers from Hugging Face. It's really not that popular. The GitHub repo has like 6 stars, but I don't know. I read through it. It seemed kind of interesting. It seemed somewhat mechanterpy. They're doing internal circuits. And then when I read through it, I was like, okay, I don't think this is actually going to go anywhere, but it makes a lot of cool points. It seems fairly like applicable. Like it's a pure applicable use case of mechanterp. And I don't think it'll go anywhere, but it's cool background research, a lot of interesting aberrations and stuff. So I thought, why not? Let's go through it. So basically, can LLMs predict their own failures? Self-awareness via internal circuits. The key thing here being internal circuits, right? So they talk about a few different ways of having LLM as a judge to detect hallucination and stuff, and the issues with those, and then their proposed solution. Then they solve one very niche problem with like a whole bunch of architecture stuff, which is pretty deep research, and it works pretty good. Yeah, they talk about hallucination probes as well. So there's like four things in here that we can talk over. There's intrinsic that they want, or where is it? This is what they wanted to go for. But then there's four types. So there's like text-based confidence and self-critique. So this is where you kind of look at token probability. So how confident are you in your next probable token? That's one approach that currently exists. They talk about the cons with it and some of the latest research. I guess if you're also interested in like hallucination detection sort of stuff from a research perspective, they cite a lot of pretty good papers. So like apricot is a cool state-of-the-art method here. It works with distillation and stuff. But one of the cons of text-based confidence is when you look at your confidence score of your next probable token, you can't detect confident hallucinations, right? So stuff where you're very confident, where you're where you're confident but you're still wrong, that doesn't get detected. Then the other state of the art is this sort of distillation apricot work. In that you have out of context and you have high training costs, so it's not as applicable. I wonder if this can be turned into an API. That's exactly what I was expecting here. The other thing to note with this approach is that you do need model weights, so you can't just do this on like a closed source model. But this, like, I was looking at this, I was looking at these two authors. This guy's a professor. This guy actually works at Huawei now. He's been at Huawei for 2 years, but he's doing his PhD at University of Alberta. I was like, good fire should hire this guy. This is very much wrap it in an API, serve it. It works very well. It's state of the art. It's on hallucination detection. So we're talking about the four approaches. One of them is that text-based confidence. Second is internal signal-based indicators with linear probes. So someone shared a linear probe example of this. Problem with this is that they're static in where they probe, right? A big thing that they know, and they do revelations about this, is that you need to look at the whole trajectory. So oftentimes hallucination can happen early in the model, and we need to look at all hidden states, so all attention patterns. So that's a con there. Probes only look at final token states. That doesn't work. And the other fun thing that they can do is that they can predict early on in generation. So another high level before kind of answering this question is what they're doing is they're training a little 5 million parameter like model. They're adding not a model. They're adding 5 million parameters with this little architecture into a model. They test four models. They test a few small quens, I think a small llama, and then GPT OSS. They train in a little detector. They have a hidden state encoder and an attention circuit, and then they concatenate these, and then they have that trained as a binary classifier on hallucination. And some fun stuff that they can do is without even seeing the full sequence, they can predict whether it's hallucinating, and that's an emergent capability. They don't explicitly train that. They just notice that even when only 40% of the sequence is there, we're already 90% confident that this is hallucinated. So there's fun stuff like that. The other thing that they're doing here that's novel is since they're probing in with a circuit on attention, they're basically taking every attention map at every layer, and that would scale quadratically, but they want this to be very computationally small. So they have some fun encoders that encode all this stuff down to a consistent linear scaling, and it's irrelevant of context size. But we'll go into all that architecture stuff later. But basically, the question is, can we probe our own model? Can we look at the model internals and predict whether something is hallucinating or infactual just by looking at the model itself? Can we keep it lightweight, not add inference burden, and can this thing kind of scale? Turns out, yes, 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 it can. Some other fun stuff they find towards the end is like this can work across model families. So you can train this on a Quen 1B, apply it on a Quen 20B, and it still works. A lot of fun stuff there later. But honestly, a lot of the meat of this paper is their architecture research. So as opposed to high level stuff, we might dive in a bit deeper there. And of course, feel free to pause wherever, and we can kind of slow down and go back over stuff. It's not the easiest to grasp. But yeah, they introduced this method called Gnosis. They have an open source repo and everything about how it works, how to do it, how to apply it. And basically, what you're doing is you're adding negligible inference cost. You're freezing the LLM backbone. You're adding 5 million parameters, and you're basically independent of the sequence length. So whether you're operating on short sequences, long sequences, you're able to have a binary classifier about hallucination. They test this thing. It works better than LLM as a judge using like Gemini 2.5. It works better than probing, better than self-consistency. Self-consistency is basically where you do a bunch of samples, like you generate 20 samples, you see if there's an aggregate match. It works better than all that stuff. And yeah, you can kind of just deploy this with low training costs. The training cost for this was like 25 bucks. They used two A100s for like 12 hours. So low training cost, doesn't mess with anything, has 5 million parameters, can be done before the full sequence is even generated. And yeah, all this stuff kind of works pretty well. But being small university research, it'll probably never get picked up or slapped into an API, even though you could really slap it into an API, right? It's just fun to see. And this is happening on model level outputs, not on like agent harness checking agent steps. This is just model generation. The other fun stuff, it generalizes to zero shot stuff. Yeah, so okay, intro is kind of some of the background of what happens. So, LLMs hallucinate, that's an issue, particularly in long horizon reasoning, and we want compute aware control. So, some of the issues with some other approaches are that they're very computationally expensive, right? Like when you run a second model of an LLM as a judge, if you're hosting this thing offline, well, now you need to host a second model, right? Self consistency. When you do multiple generations, you have to do more calls and stuff. Someone's asking if Unsloth teams and stuff will bolt these into open weight models. I think it would be cool, right? Like one, the fact that you can do this if you're deploying yourself. Two, this reminds me of stuff like Llama Guard, and OpenAI had a version of that for GPT OSS Safeguard or something. Like, why not do a small bolt-on approach like this, right? If people extend this, it would be pretty cool to see. And you don't even need to serve it as its own API, right? You're not changing the LLM background at all. The LLM backbone is the exact same. All you're really doing is returning an additional binary classifier with confidence of is this hallucinated or not? And that's output at every single token step. So, if you pass the threshold, you can just cut it there. And this works better than every other approach that they've tested so far. And they do a lot of ablations of this. So, okay, prior work. There's text-based self-critique and confidence estimates. So this is basically where you infer correctness from generated tokens or token probabilities. So this is more so tracking linguistic fluency rather than reasoning validity, right? So as you're predicting the next token, you're just kind of sequence completing, right? Does this next token make sense? Is this the next one that should be here? Probably sounds about right. That's more so like based on fluency and stuff like that. But it doesn't work as well, especially on long tasks. Multi-sample consistency methods are basically where you estimate confidence from agreement across multiple generations. So this improves robustness, but at the cost of inference, right? So if I have a question, say a medical diagnosis, what if I shoot this through 10 models and see, do we have conciseness? Do they all agree? If they do, fine, we'll pass the answer on. And that's our sort of guardrail. Problem there is you have the cost of improvedness, right? The cost of inference there. Their eval scores are pretty compelling. Curious how this performs in something like healthcare. Yeah, it would be interesting to see how it performs. Right now, they have a pretty diverse set of evals. We'll go over them in a bit. What else? External judges and reward models. So external judges are, pretty complex. So they talk about a state of the art 8B model. I'm forgetting the name. And at the time, Gemini 2.5. This paper came out this year. It came out January 4th, but they're using Gemini 2.5 Pro. But it's fine. They probably just did this research a little while ago. But yeah, their little 5 million parameter model, their little 5 million parameter addition of weights outperforms Gemini 2.5, state of the art 8B, LLM judge trained models, all just for 5 million parameters. And that, of course, the problem there is like, we're not looking to outperform, right? You can get like 92% there, 95% here. The difference is you'll have significantly faster latency. They talk about the speed up there, and of course, cost. And the other models don't have access to external features, right? So if you're doing RAG, for example, this is already using what's in the model's weights and in your augmented generation, whatever your retrieval data is. But an external judge like Gemini 2.5 might not do that, or you can't pass in external data, right? Um, Someone has done quite a bit of work about probing detection. Maybe you can talk about it. Feel free to interrupt whenever if you want to share your work. It's one of the approaches similar to this. So looks like someone in the Zoom has done quite a bit. Pretty exciting. Um, in this thing, they want to see, okay, can models reliably predict their own failures by looking at internal signals to during the generation process? So they have this process called Gnosis. It's a self-awareness mechanism that endows frozen LLMs with intrinsic self-verification. They don't need external judges. They don't need external models. They just add in some weights and kind of works. And then at the end, they have a binary classification judgment head. It just gives a correctness score. Um, we'll talk about this in a bit, but here's some early evals. So logic entropy is kind of the worst performing. It's where you kind of just look at, okay, what's the probability of the next likely token? If it's not high enough, uh, someone's asking, how does this bolt on architecturally, how does this bolt on compare to MOE? It bolts on. It's just separate from the current architecture. Like you're not adding in steps in between attention. You're just reading masks and then doing stuff on the side. So I can show it in the architecture here. Basically, like if you've seen a transformer diagram, say you have like right here to the side, you have your entire MOE model or whatever it is. You have a bunch of transformer feed forward layers. This is just tangential to that. So you break off here, you read in hidden states at the last layer, you read in all the attention, then you do this on the side, but you're not touching any of the proper LLM. It just kind of bolts on, right? So the model itself is frozen. You're not touching anything there. You're just branching off and additionally computing these 5 million parameters. So that's how you can just kind of bolt it on. Um, let's see. Yeah, so performance here based compared to logic based Skywork RM. That's the state of the art. Train a judge model compared to Gemini 2.5. Their thing is pretty state of the art across math reasoning, open domain, and a general academic knowledge benchmark. It actually judges quite well. And then they test this across a whole range of broader benchmarks. We'll get to it here. Pretty exciting stuff. So I think they do some more background here. The intrinsic capability of this being like done internally in the model, it allows for early detection of failing reasoning trajectories. So, as you're scaling, as you're generating, you can determine and cut off generation early, right? So if you have something super low latency and after a few tokens, you've generated that this thing is hallucinated, it's not correct, you can already cut off right away. The other thing is it's efficient across model sizes and domains. This thing doesn't scale with sequence length. They keep that consistent and they do a lot of work to do that. It's very compute aware in the sense of it's only 5 million parameters. And yeah, so here's their main contributions. One, intrinsic, it freezes the LLMs, allows it to work on itself. Two, dual stream interception from hidden states and attentions. It's global, right? So it's not just looking at it's not just like a probe that looks at the final hidden state. It's dual stream. So it looks at the last hidden state layer, and it looks at hidden states across all of attention. They compress that down. They do some cool stuff there. Early failure detection, we just talked about that. This is actually an emergent capability. They do not train this at all. They just train with binary classification on labeled data. And this thing itself can, it emerges in the sense that it pretty early on, it's very confident and surpasses benchmarks at just determining with 40% of the data. And last is, of course, it's state of the art at small scale. They had 5 million parameters. It outperforms stuff orders of magnitudes bigger. They test against a 8B reward model that's specifically trained for this task and proprietary judges across these different benchmarks. And it works across multiple models and all that stuff. Okay. Related works. I don't think there's too much for us to go into here, but if this is your domain, if you're interested in this stuff, these are all pretty good words and topics to know and papers to read through if you're interested. So external reward models and judge LLMs. This was like kind of the word of 2024, right? 2025 was year of agents. Every year is kind of the year of evals. LLM as a judge works, it doesn't work. There was a whole bunch of talk about that. So there's a lot of research that came out. But basically, other work is to do external verifiers, right? You can train separate models to score response quality, factuality, stepwise correctness. And they're used for ranking, hallucination detection, guided test time search. Here's different data sets that do that. Here's different papers, reward bench, all that stuff. These models provide strong signal, but incur substantial annotation cost and inference latency and deployment overhead. So one, you either need to have a lot of inference latency by using a big proprietary model, or two, you have to, use a whole data set, train a custom judge model, and then that has a lot of overhead for deploying it as well because you need to serve multiple models. Second is this text-based confidence, so token probabilities, max probabilities. This has issues of confident hallucinations and out of distribution stuff. Papers you should check into. Apricot is a cool method. It works with some distillation. Next one, internal signal indicators based on linear probes. We have someone that has worked on this, so I guess they'll talk about it later. But basically, you're doing probing, probe and see how well it does. I'll save this for someone else to discuss. Multi-sample, self-consistency, and test time scaling. This is the last one. Inference cost that scales with the number of samples, often saturating long what is this one? Multi-sample. Oh, multi-sample and self-consistency. This is basically where you aggregate over multiple calls, right? So maybe I send the same query to 5 models. I use, Grok, OpenAI, Anthropic, Gemini, and Llama. And then if they all agree, then I send it. That's one way of having your thing. But of course, we know the issues there, right? You can't stop early. You have high cost there, but it does work. Okay, all that's cool. What's their method? So Gnosis, it's a lightweight self-awareness mechanism designed to retrofit frozen LLMs with introspection capabilities. It operates under the intuition. This is one of the key. These are the two intuitions that you need to kind of follow. Um, Model's internal states that a model's internal traces, its evolving hidden states and attention routing patterns carry distinctive fingerprints of hallucination and reasoning errors. So this is some of the intuition that they believe in a model's internals, hidden states, and attention routing patterns. There are these, hidden detective distinct fingerprints that we might be hallucinating here, or there's some reasoning error. And if they can prove this, they can somewhat prove the alternative as well, right? So we'll go into that later. Unlike external judges that require separate, expensive decoding passes, it's a passive observer. It compresses the backbone internals into signals and compact descriptors and fuses them to predict the scalar correctness scores. So unlike other judges, it is fully passive. You can run the LLM and ignore all of this. All it's doing is just pulling outputs from there, adding 5 million parameters. The architecture is explicitly designed so that its inference cost is independent of sequence length. The next 20 minutes is going to be a talk about this. Basically, they do a bunch of like novel architecture research about condensing down quadratic scaling attention to consistent scalar. And they do this all to add negligible overhead, even for long context. So problem setup: length invariant outputs. Ooh, someone's writing on the screen. Let's see if we can turn that off. Okay, I give up on turning it off. But anyway, there's kind of I took some side notes here. Oh, I lost my sticky note. GG. Okay. Basically, here's the architecture. So there's two sides to this. One is a hidden encoder circuit, and the second is an attention circuit encoder. So hidden circuit encoder, we'll go over how they define it. So the inputs and the outputs. So let X actually I'm gonna take a pause here before we go into this full architecture. Does anyone have any questions on what we've talked about so far? What are the other methods? What's their methods? What does any of this mean? Before we kind of go into the meat of how this architecture works. Feel
Yeah,
free to yeah.
yeah. One comment on the probes. I've done some work on probes, and I think this method would be much better than probes because the probes uses one level of, let's say, head number 33 or something like this, and takes the weight hidden states from that head and uses a single neural network to predict the probability. I think this is more complex and more comprehensive. So this method actually uh, beats probes just, just because it has
Yeah,
more parameters.
yeah, very much appreciate the like background info there. So there's two big things they do here. Basically, they are just taking the hidden dimension, the hidden state at the final layer, but the other thing they do here is they add the attention maps across every layer in the model, which that's where it starts to get pretty big. So there's a lot more going into this thing. Yeah, okay, so let X denote the input prompt of length S of X and Y is the generated response. So basically at any timestamp, you're passing in the entire input and the generated output so far. The input to Gnosis is concatenated sequence with a total of this and this. So you concatenate input plus output generated so far. The backbone has hidden dimension D with all decoder layers and H attention heads per layer. During generation, we read only the final layer hidden states. So half of this architecture diagram is about the final layer's hidden states. The other half of this diagram is about the attention maps from all layers, layer 1 to layer H, where they're of, S by S. So it's each of these is layers times number of the attention spaces. So this is kind of where if you do it blindly, you'll scale with your sequence length. Your attention quadratic complexity also affects this. So what they have to do is kind of scale all this down. And then the output, like the learning verification objective they're doing, is basically the probability distribution that the answer is correct and this is just the parameter. So you're optimizing your parameters based on last hidden state, attention maps to be a binary classifier. So your output is your weights given your model's final hidden state and all the attention maps to predict 0 or 1, basically. Um, First thing they need to solve is fixed budget compression. So to decouple computation cost from sequence length S, we use projection operation that maps variable length traces into fixed size tensors. Basically, you have we use a projection operator that maps variable length traces into fixed size tensors. So this scrolling is really weird because they randomly added this table here. Sorry, it's a little weird to read. And then they have attention maps. Each attention map. So attention maps are basically you have queries and then key value pairs at every layer. They get downsized via adaptive pooling, a fixed grid this, giving a standard set this. All downstream encoders operate only on this dimension. So I think instead of reading this, we can kind of look at the diagram of what happens here. So this is one of the hidden state encoders, right? You input the hidden state of the last layer. From there, you do some projections. You do 1D CNN pooling. Then you have this convolutions, mixing. This is all fun architecture stuff that's talked about in the next section. From there, you have this feature aggregation. You have a set attention block, pooling, mixing set attention, flatten it, output it, and you end up with a linear scalar. So whatever the hidden dimension state is, they do all this fun architecture, and you output just, okay, here's our hidden state dimension. Same thing happens on attention maps. So you have all these attention maps, they're S by S dimension, downsample them, reshape them, do some feature extraction. We'll talk about what the architecture for this is later. One of them, I think, is a CNN. You treat it as an image. The other one is some cross attention. Then you do a linear projection across both of these. From there, you do this you do convolutions on that, you do pooling multi-head attention, flatten it, then you have an MLP, then you have another straight dimension. All this architecture, you have your final hidden state, you have your attention maps. All they do there is just concatenate them. But okay, let's go into some of the details of how they do this. Okay, so hidden state encoder. This is basically what we pull in from the current frozen LLM is the hidden state of the last layer. So instead of looking at logits, we want to do that. So a small encoder maps this latent trace into a compact descriptor. So what they're trying to do here is basically, can we condense it? Can we map a summary of this final hidden state into a smaller, like consistent representation? Turns out we can. So there's a local temporal encoder. It's a lightweight multi-scale 1D depth-wise convolution over the sequence. So you have a sequence, it's your last hidden state. First thing you do, apply a 1D convolution over the sequence. Then you have this global set encoder. To summarize the sequence into a compressed representation, we apply a set transformer style encoder, another encoder. Then we have set attention blocks, followed by multi-head attention block. This engages global interaction across all positions and aggregates the sequence into a small set of summary tokens. That is then flattened. Then you do linear projection into the final hidden state, which is of just Z dimension. Basically, that just explains all of these steps, right? You pull this directly from the model. You do some linear projection. You do that 1D convolution polling. Then this is your local global stuff, this pooling, all this fun attention, then you just re-summarize it. So this is very deep definition of what architecture stuff is. But if you're actually implementing this, all the code is there. You can ask your favorite LLM, what are set attention blocks? What is pooling multi-head attention? What are set transformer encoders? You can learn all this stuff. Then that's one half of Gnosis. The other one is the attention circuit encoder. So the attention stream reveals layer and head level routing patterns that can indicate brittle and unstable focus, completing the hidden state descriptor. Rather than feeding the raw attention weights into a large network, they kind of summarize each downsampled attention map by by mapping it into a compact feature vector. So they want to take all these attention maps and map them into feature vectors. The key thing to note is that they're taking every layer's attention. So it's across time, across the whole model. Did they need to do this? Yes. They did a lot of ablations on, okay, what if we only do this side? What if we only take the final hidden state, get rid of this? How does it perform? It works for some benchmarks, it doesn't work for others. What if we only did attention on some layers? What if we didn't do it across the whole thing? What if we do it on the whole thing? What if we don't do this? This is what they found to be optimal and what worked the best. So yeah, you're basically downsampling all these attention maps across all layers to a single compact vector. The main thing this solves is scaling complexity, right? Because as you have more tokens generated, you have more attention maps, right? These attention maps grow with the number of attention computations. So if you have 2048 as your token length versus 128,000 versus a million context, you're going to have a lot more attention maps, and then that would slow this down, right? So the background of what they're trying to do is we need to scale these down to a fixed compact feature vector. How do they do that? Basically, this fun attention, this fun architecture. We'll go through it line by line real quick, but we won't really go that deep. So there's two complementary approaches. One is a lightweight CNN that treats each attention map as an image that learns local to global patterns. Two is an interpretable statistics-based extractor that summarizes how attention is distributed. So part of this architecture is a distribution calculator, basically. It concentrates and it shows how local or long range different attention features are. So you have these two stages. You have that CNN and you have the other statistical distribution calculator. From there, this measures the spread in textures. Diagonal is this, locality, lightweight center spread measures this. This is all technical stuff of the architecture. It seems pretty interesting. And then here's that key thing. We ablate each variant in their hybrid architecture later. While two extractors individually are competitive, the hybrid is the most consistent across benchmarks. We adopt this in the final design. Cross-head, cross-layer encoding. We arrange the per head summaries. So right now for each head, we've kind of done this summary for so far into a grid. Those grids are then condensed down again. We add each learn layer and head embedding to preserve depth and identity. Okay, a lightweight encoder mixes information across layers using layers and heads using a few axial convolution layers. This design is substantially cheaper than full global attention over the full head. Finally, we apply a mixed pooling attention. So, okay, here you have every single attention map, right? So if there's 42 attention layers, you have 42 maps. Downsample them, reshape them, do this two-style feature extraction, a CNN and a statistical thing. From there, you're left with a grid. Your grid is of size L by H. You have one grid per attention layer. The next step we need to do is, okay, over time, over our model's depth architecture, what happened in each different attention layer? What can we learn from there? So we need to do a sort of pooling across them. That's where they take this cross-head and cross-layer encoding. So from the grid, they want to apply, they do more convolution layers, basically. It's cheaper than full global attention. That's this part. Then they flatten it, have an output MLP. Frankie, you have a question?
Yeah, Vipul. Quick question. So the hidden circuit encoder is kind of like just picking out some features or the important features from the hidden state, correct? Across different layers as well. Um,
The hidden. So are you talking about
yeah.
this one? The
Yeah, the
hidden?
hidden
No,
circuit, yeah.
this is just the final.
Oh, just a
The final.
final.
The final. Yeah. So it's
Okay.
specifically just the final. So I can point to it in a second, but yeah, it's just the final hidden state.
Okay.
And
But
then
then okay, so go ahead. Yeah.
no, that's basically it. So that's the final hidden state is used for attention. They use all of the attention layers. So
Um,
final layer hidden state.
Yeah, so a quick question here. I mean, just trying to figure out the intuition here. Why do you think that they chose to look at the attention maps as having some kind of feature to tell whether or not you're hallucinating or not? I'm kind of like puzzled by, well, maybe it works well, but I'm just kind of like puzzled. Like, why would we think that that has interesting information?
Yeah, they actually go into the exact reasons for. So that's the fun thing with having this architecture, right? They basically point out, okay, this little part is, attention over local features. This is us over this. So I can dig into the specifics here, and they kind of explain that in each step, which is why I thought this paper was kind of interesting. The intuition as to why this would happen, it gives you a bit of a high level of, okay, we're computing what tokens have relation with each other at different layers in the network, right? Now, if we're generating stuff, but we're not really looking at, okay, this generation didn't really use what it should have at this level in the layer, something seems off. Maybe we can determine something from there, right? But we can take a second and find where it talks about what each part of this architecture looks at, and it helps paint that intuitive picture a bit. If I can find it real quick, we'll read over it. Otherwise, I'll just come back to it at the end of the paper, which is, we're almost done with it. So CNN treats each attention map as an image and learns local to global patterns. Interpretable statistics summarize how attention is distributed. So they're looking at local to global patterns of attention, attention distribution, where it concentrates, how local or how long range different attention is at different layers. Concretely, this measures the spread in texture, so entropy and frequency based of features, diagonal and near diagonal mass to capture locality, so locality of stuff, lightweight center and spread measures that describe the average location of attention and how widely it is dispersed. So they're like, honestly, I don't have the clearest understanding of what all these mean, but clearly, they have a goal to measure specific parts of attention, right? So, how is it distributed? How is it concentrated? How local or long range is it? How widely is it dispersed? And then they talk about this a little later in the ablations, but it seems like they have these measures of attention per se. So is your attention distributed? And alongside that, looking at your final hidden state, if you're making claims that don't match with the attention set it should have, maybe there's some connection there of why you've hallucinated. But yeah, it's like a good mental question that I think everyone should think a bit more about, right? Like I don't have the best explanation here, but do you wanna chime in?
Oh no, I just want to. I think you might have touched upon it already, but I just want to go back to it. That is for the different layers, right? Um, is there how are they capturing the sequentiality of like looking at the attention map of this layer versus subsequent layer, etc. Does it matter the sequentiality, or I'm just trying to understand like how they capture the factor. There's a progression, right? So I have attention on this layer, and the next layer has some
Yeah.
correlation with the previous one. So how do they capture that?
So the first step of this downsampling is done. Basically, this half of the architecture is done per map. So it's done sequentially on every single map. Then they kind of put it in a grid formation. So cross head and cross layer encoding. We arrange the per head summary. So basically, here everything before is done per head, right? It's layer by head into a grid. So layer one, head one summary, layer one, head two summary, layer three, head three summary. And then now, this grid, if you were to sort of draw it out, this would be over time, right? So first layer, second layer, third layer, fourth layer, fifth layer. Then from there, this is some of the cross layer convolutions that they're doing. This they could do attention over that, but this architecture also works. So a lightweight encoder mixes information across layers and heads using a few axial convolution layers. This design, like they slap a CNN on stuff across layers. I don't know enough about that, but apparently it works. Because the stage operates on fixed dimensions, the compute is independent. I think they talk about this later in another section. We'll get back to it, but that's kind of what they do. So they have a ordering of matrices. So it's per layer, per head summary. Then they do sort of that cross layer summaries with this CNN, and it learns stuff across layers.
Okay,
If
thanks.
I'm not mistaken, it is explained. somewhere down here.
Yep. Thanks.
Per map CNN. Okay, so downsample each attention head to a fixed K by K grid, extract per map CNN plus statistical features, mix across layer by head grid with a lightweight axial processor pool to obtain Z attention. Detailed description of this. I don't know, maybe someone else while we're reading through this, so we have time, look into this circuit. If I'm not mistaken, they do talk about it somewhere. Then the next thing they do is this fusion. They ablate whether they need both of these. It's the easiest part of this architecture. How do they fuse it? They just concatenate the two descriptors. So you have summaries here of the last final state. You have summaries here of all the attention layers and across attention thing. Just concatenate the two, feed that into a small gated MLP head, and that's kind of it. The whole architecture of this is intentionally small. The two things that they've solved here is the attention is no longer quadratic scaling, right? It just scales with the amount of attention layers, so it's more linear per se. And all this adds 5 million parameters. It's 1,000x smaller than 8B reward models and significantly smaller than 2.5 as a judge. Okay, training. I guess I'll pause again. Any other questions, comments on this before we get back into it in the ablations later? Okay, cool. I'll continue then. Training. Training is cheap. It can be trained without costly annotation data. Basically, all they need to do is generate answers and you have ground truth. Then you have predictions to ground truth, right? So you just need binary classifiers. You just need to see whether stuff is accurate or not. And then it's trained to minimize binary cross entropy. So the LLM is frozen. Gradients only flow through these 5 million encoders, 5 million parameters of encoders and the fusion head. And then you have a binary cross entropy loss. So, true or false, basically. They talk about the data set and stuff in a second too. Experts and results. I guess, okay, we'll talk about results first. So they want to evaluate it in three practical regimes. One is self-judgment, where each head scores generations from its own frozen backbones. Two is sibling model judgment, where small head serves as a lightweight reward model. Three is early correctness prediction, where we want to see, can we do anything with partial completions? Ted asks, is the loss only calculated on the final answer / token? This loss is calculated with the input of the input tokens plus the generated, and it's calculated per token output, right? So if I have a short sentence, like 8 words, and I'm generating 6 words, I'm calculating this at every token, right? So you're kind of calculating that answer at every answer, every token generation, if I'm answering that correctly. Okay, backbones. So what are the models they apply this to? Qwen 1.7B hybrid, Qwen 4B thinking, Qwen 4B instruct, 8B hybrid, and OSS to scale up. The backbone weights and decoding settings are never updated, so they freeze the foundation models. All they're doing is training their little 5 million parameters. How do they do that? They have training data. It's a mixed math trivia corpus to cover both multi-step reasoning and open domain factual recall. For math, they use this DAPO Math 17K, 14K completions. For QA, they subsample 40K questions from Trivia QA. And there's one more I forgot to highlight. But basically for that, training and details costs, we train each head for 2 epochs over this mixed data set, learning rate of 10 to the minus 4. For the largest backbone, the GPT OSS 20B MOE, the full pipeline data generation and training finishes in roughly 12 hours on 2A180 GB GPUs. It's about $25 for the big one. Small ones train faster. So very cheap data set, very easy to label. You're not doing any crazy labeling. You're just pulling from labeled data sets. Okay, benchmarks. They test on 12K tokens. Here's all their benchmarks. They stress multi-step reasoning, hallucination detection on short factoid answers, out of distribution generalization. Metrics, they have a whole bunch of metrics. They test this thing very well. AUROC, AUPR, AUPRC, AUPRE, Burrier skill, all this stuff. Baselines, there's 4 baselines. So they test it on statistical internal scores. So logit entropy, mean token probability, attention, eigenvalues. They test on trajectory injections. They test on external judges using state-of-the-art public reward model. So Skywork RM Llama 3 8.1p. And then another Quen one, as well as Gemini 2.5. They tested on probes, all this stuff. I think we should scroll up to the results. Yeah, this was weird that this table is up here. But basically, here's the different measures. Here's the different models they trained on. Domain one is math reasoning with these data sets. How does their thing perform on hallucination detection compared to everything else? So compared to mean probing, compared to specific judges, they're killing it. They're doing very, very good with 5B parameters, basically better than everything. Gemini 2.5 is slightly better on OSS for some math verification. But you got to remember the overhead here is pretty killer. And then across the board, they're kind of killing it and everything. So general domain stuff, math reasoning, knowledge reasoning, MMLU Pro. MMLU Pro, I don't know, Gemini 2.5, some of these are pretty good, but things pretty good. Going over that, let's continue through real quick. Where were we? Self-judgment, we evaluate it in self-judgment steering, consistently outperforms training-free baselines and large external judges. Superiority over internal baselines. Okay, efficiency and scale. With only 5 million parameters and negligible overhead, fixed overhead, it matches or exceeds something 1,000x better, larger, and Gemini 2.5 Pro. Maintains near consistent latency and achieves roughly 37x, 99x speedups over 8B reward model and judging at 12K and 24K tokens. This is like the reason for why not slap this thing in an API, right? It's significantly faster, near constant latency at long context. It's better performance. Like all this stuff just works pretty well. Bimodal peaks. So they start to talk about issues with other reward models. So where they peak at correct and incorrectness, they have sharp peaks. So their thing is very binary, right? It's either correct or incorrect. Which chart was this? Whereas other ones have a bit more of a spread, which is what we don't want. I lost where I was. Yeah, okay. Anyway, that's enough on evals. We'll come back to it if anyone has other stuff. I just want to finish real quick since we only have 8 minutes. Last thing, cross-scale zero-shot reward modeling. This is pretty exciting. Sibling modeling, where we train Gnosis on a small, cheap backbone and deploy it to adjudge larger family members without fine-tuning. So they train the 1.7B and it transfers effectively to 4B and 8B siblings across all domains. On math, it's 93% AUROC, and it matches nearly the 96% on self-trained head. So, this thing transfers from small model to big model pretty well. This transferability implies that this is another interesting mech-interp general LLM take, right? This broad transfer implies that hallucinations manifest as structural invariance across model scales, offering a free lunch where a small model head serves as a supervisor to the entire model family. So if you're doing safety work, if you're trying to do some of this factual analysis, right? If you want to see what do models know and not know, if you look at the same family in smaller sizes, these things transfer up to large scales, right? So these hallucinations, they manifest across model scales. So as much as we've assumed a lot of hallucination and stuff gets fixed by larger model scale, not exactly, actually. Models are still consistent in their inaccuracies. It performs best when the models also align with their formatting. So you don't want to transfer from thinking to non-thinking, like thinking to instruct or thinking to non-thinking, base to base. Be smart. Stay in the same reasoning to reasoning and stuff. Next section, early error detection. I've talked about this enough, but it's emergent. It's trained exclusively on complete trajectories. It generalizes zero shot to partial prefixes without additional fine tuning. So this is kind of the claim for that, right? Or this is the proof of that. It reaches near peak accuracy and positive after only observing 40% of the generation. In contrast, external reward models and single token learnable probes typically require full responses to stabilize. So, this is just pure emergence. You train on the full output every time. After seeing 40% of the generation, it's near peak accuracy. Pretty crazy. This enables aggressive compute aware control policies, right? So say I'm using my MacBook, right? I'm on this Zoom call. If I was to open up Llama CPP or Llama run GPT OSS 20B, throw this paper in, my laptop will freeze, right? My laptop has 36 gigs of unified memory. If I load a 20B model, send in 10,000 tokens, my laptop's cooked. It can't handle a Zoom call, my screen, and that. But something like this, right? It can cut off generation as it's generating if it sees it's hallucinating stuff pretty early. Very useful application, right? So I want that aggressive compute aware control policy, right? My laptop will basically be non-functional as it generates stuff, and I don't want to waste compute as it's hallucinating. So very cool stuff. And of course, all the code is out there and stuff. Okay, section 5, a bunch of ablations. First one, do they need to do both streams? Do they need this is what Frankie was talking about. So attention is most useful for long form reasoning. Trivia QA, hidden only dominates, fusion adds a little. Hidden states carry most short factual reliability. This intuitively kind of makes sense, right? You're only looking at the final layer, but you've kind of aggregated all previous layers. Attention is useful for long reasoning. This could just be because you're only looking at one hidden state. You're not looking at them all. Fusion is the best performance. They talk a bit more about this and that. Attention map extractor. We ablate how to summarize each downsampled attention map with a lightweight CNN. CNN and stats. This was the final design. Additional ablations. How do they do grid mixing? Identity embedding, pull strategy. So this is kind of more about all that stuff. I think we can read into it later. Discussion and limitations. It's an efficient self-evaluation framework trained on a compact model, efficient framework for self-evaluation and sibling modeling, where a small head trained on a compact model effectively judges larger models with the same family. That's exciting. So self-evaluation judges larger model families. There's that emergence, it's self-aware attention, transfers, not capable of acting. It is not capable of acting as a universal zero shot because it doesn't work across unrelated architectures. Okay, conclusion. Despite only adding 5 million parameters, it consistently outperforms billion parameter reward models and large proprietary ones, demonstrating high fidelity correctness signals and intrinsic to the generation process. Cool. Okay, that's the paper. I hope this was like somewhat fun, useful read for people. This is pretty different than most papers, a lot of architecture work, but I don't know. It's just fun, right? It's like something that works so well that we'll probably never see, but fun intuition to read behind. And it's fun to see how, like, training this stuff on small families still extends to larger models in the same family. Anyway, I will pause there from my yap. We have 2 minutes, and of course we can go over, but any thoughts, comments? I'm going to check in on chat. Any discussion, RJ asks, any discussion on how this generalizes hallucination types outside of the training set? Yeah, the whole point of the 3 data sets that they tested was they wanted to test across 3 domains. One is reasoning, one of them was generality, right? So I think that trivia QA is on general purpose diversity. So it should generalize. I wonder if we can create RL environments using this. Reward is basically length of text generated without hallucination times correctness of the response. Do you want an environment where you're rewarding length of text generated? I don't know if that's what we want. I think like most RL is done for agent trajectories, right? And you're okay being wrong as long as you can get back on track. you're not trying to optimize the number of steps. But I guess another way to look at it is LLMs are really good condensers. They'll take a lot of tokens and condense a shorter amount of tokens. They can do this with RAG, with summaries, but they're not great at generating a lot of tokens, right? So an LLM won't generate 128,000 tokens. It won't generate like 500,000 tokens. Maybe you could use this for something like long context generation, if that's what you're trying to do, like RL for synthetic data that's not hallucinated and long context. But now we're getting very niche. Maybe penalize it when it hallucinates. Yeah, I mean, creativity, whatever you think. Good paper, good. Very interesting. Lots of just-in-time learning about ML for me. So I'm doing it. To clarify, they aren't actually changing the model output here, but retaining the output but retaining only outputs with high enough scores for evaluation. Um, Travis, they aren't actually changing model outputs here, but retaining only outputs with high enough scores for evaluation. What do you mean by retaining only outputs with high enough scores for evaluation? They're evaluating all outputs. So basically, like your model, like the Quen, the Llama that they're doing this on, the GPTLSS, the model is frozen. The model is doing its full input outputs. This is just external, right? So like it's a little like you plug it into a model, you're additionally computing these 5 million parameters, and then you're outputting a binary classifier if it's hallucinated or not. From there, as a builder, like let's say I serve this as an API, right? You have your response API, you have your next token predictions. You also have hey, your thing has been hallucinated, like classifier with some confidence. You can choose to do what you want with that, right? You could go crazy and make a chatbot that only hallucinates if you want and not output anything until there's hallucination there, right? So this isn't really changing anything. You still have the same LLM. That's frozen. That's still being run activations through. This is just additionally, giving you that. He's more bullish than me. It seems like it'd have some impact free lunch for improved performance win. I'm very bullish. Like I think it's great. That's why I'm reading and sharing the paper. I think it's like cool. It works so well. They have code to reproduce it. Serving this in inference is even that hard. I just don't see like inference providers serving this stuff up, right? I don't see that being picked up. I think it's the sad fact of like even this guy, like I was like, dude, this is such good research. Someone like Goodfire should slap this in an API, serve some valuable like interp API. It's useful. I look into this guy. This guy is like at Huawei/student, not much research, not many papers, but very good paper, right? It's very cheap, very fast, very much efficient, but I don't know. Maybe an eval company shits this out. Um, can a similar approach be used while making a harness for models while they're executing coding tasks? Yeah, of course. Why not, right? Why not do this with coding? Why not see if code is hallucinated or whatever your verification metric is there, right? In this case, they do a very easy binary objective on hallucination, but that doesn't mean that you couldn't do that on a different objective and tweak the architecture a bit, right? The architecture is pretty simple. And even if you don't want to do something this advanced, right? They talk about ablations of, okay, what if we only look at the final hidden state? What if we don't do this grid attention, cross attention stuff? What if we only do parts of this? That works for these cases, but doesn't work for these. If you're doing like a tab autocomplete short use case code model, well, you can probably even simplify the attention. You can probably even simplify the architecture even more, right? Stuff like that. Um, Under benchmarks, they say and retain only Q&A pairs with valid final answer for evaluation. Okay, maybe I misread something on the output evals, but cool. Anyone else, feel free to unmute, add comments, thoughts. Otherwise, we will see you next time.
Thank you, Vibo.
Thank you.
Thanks, Vibu.
Thank you.
Of course.
Nice.
Cool. See you guys next week. I think we have a volunteer, but if anyone wants to volunteer then the following week, new year, new papers, someone volunteer paper.
I think Ted had some last word.
Ooh, Ted, let's see what Ted has said. Ted says, seems to the natural follow-up is if you use this method for task X, fake coding, and every time the failure scores cross threshold T, you override the next token and insert, wait, let me think, and then see if your performance increases. Yeah, there's like many ways to do that. That's like the S1 paper. I think this is also just like, this is just one step in LLM as a judge, right? Say this says you're hallucinating. Maybe you rewrite your prompt. Maybe you do multiple samples. Maybe you fall back on a guardrail. Depends on your use case, right? Are you in a high risk medical domain, legal domain? Maybe you just say, hey, talk to a human instead, right? Maybe it's human in the loop. Maybe you're like, you know what? Fuck it. I want to mess with people. So we never know. Oh yeah, cool. Someone volunteer papers in Discord, and then we'll continue from there. Cool. Have a good week, everyone. Take care.